Hello, my name is Eric Yanchenko, and today I'm going to be giving a brief introduction to p-values and hypothesis testing as part of a training module for the C's program here at NC State. So for this talk, I'm going to start with a motivating example and then get into some of the philosophy behind hypothesis testing before getting into more of the details about p-values, including some common misuses, and then talk about some of the approaches we can have to solve those. So I want to start with a motivating example to kind of help fix the ideas. And oftentimes when we think about hypothesis testing, we might think about clinical trial. We want to see, hey, is drug A better than drug B? And those are really important, definitely. But with this example, I kind of want to argue that hypothesis testing is something we do every day, even if we don't realize it. So for this example, you have this hypothesis and you think that you can get away with speeding on your way to work. So you're a smart scientist, so you decide to set up an experiment. And so what you're going to do for the next year, every day, you're going to drive 10 miles an hour over the speed limit. And you're going to record the number of tickets you get. And so then at the end of the year, you have to decide whether you think it's worth it to keep speeding or not. So let's kind of break this example down. So what are some key points? Well, we have a hypothesis, and that is I can get away with speeding. We have to have some data. In this case, it's the number of tickets we get in 365 days. And then ultimately, we have to make a decision. Should we keep speeding or not? We can't really have it in between. And so for each of these, there's kind of a lot going on. So why did we choose this to be the hypothesis? We had a lot of choices of data to collect. Was this the best choice? How are we going to analyze the data? How are we going to make our decision? And then what are the consequences if we make the wrong decision? And so I think we should just be kind of thinking about these as we go through the talk, that for each decision, for each layer of the hypothesis test, there's kind of a lot going on. So now let's get into some more of the specifics. It really starts to help with a fundamental view of what statistics is. And so there's a nice quote here that statistics may be defined as a body of methods for making decisions in the face of uncertainty. And so this is really key. In all of statistics, it's about how can we make decisions? We have data and we need to make decisions, and there's going to be uncertainty. And so we kind of have this paradigm of we have a hypothesis, we collect data, and then we make a decision. And so hypothesis testing is going to be a really fundamental method for this setup. So I kind of break down hypothesis testing in this way. So the first thing, the most important thing, is we need to develop a scientific question that we want to test. So in our example, it was, can I speed without getting caught? But there's many things we could think of. Does smoking cause lung cancer? And many more. So this is kind of the scientific question of interest. But then step two, we need to formulate this hypothesis into something that can be tested statistically. And this can be really hard, right? We have to take something that's just a purely scientific question and then formulate it in a statistical way. And when we do this, we'll have a null and an alternative hypothesis. So the null hypothesis, this is kind of the status quo. This would be kind of the baseline. Maybe it's the old drug treatment, or just kind of the baseline. Whereas the alternative, this is what we want to prove. So if we want to show that our method is better, then we need to put that in the alternative. Or in our case, we want to show that I can get away with speeding. So that needs to be our alternative. And hypothesis testing is set up very similar to our judicial system, where it's kind of innocent until proven guilty. So it's the null hypothesis unless you can prove the alternative hypothesis. And so this step is really important too. It needs to be done carefully, how you're translating your scientific question to a statistical question, making sure you keep track of the null versus the alternative. And so then from there, you need to derive a test statistic and its distribution. And so maybe this is the mean of the data. Maybe you just take the largest observation. There's many things that could be the test statistic. And then ultimately, we need to determine a decision criteria. What are we gonna decide about this test? And so there's some key language here. You either reject the null hypothesis or you fail to reject the null hypothesis. There's no accepting the null. Again, it's similar to the courtroom. You're either guilty or not guilty. You're not proven innocent. You're just proven not guilty. So here we'll either reject or fail to reject the null hypothesis. And so I just want us to see that each of these steps, there's really a lot going on. That it might be a simple statement, but there's a lot of thought, there's a lot of statistics, and even a little bit of philosophy behind each of these steps. So Let's look at our speeding example now. First, I need to define some notation. So we're going to let theta be the true probability of being pulled over on any given day. And this is kind of the unknown parameter of interest. If we knew this, there'd be no point in running an experiment, but we don't know it. And so we're going to try to estimate it. Our test statistic is t. That's the number of tickets. And so this is a random variable, and we need the distribution of it. But then t star, this is the number of tickets that we actually receive. So you can kind of think of this as a realization or a draw from capital T. So this is data. It's what we actually observe, and it's not random. Once we collect the data, this is fixed. And so here we're going to naturally assume that t is a binomial with the number of draws 365 for each day and a theta probability of being pulled over. And so here even there's a lot of assumptions going into a binomial model. For example, we assume that they're independent and identically distributed draws from a Bernoulli. So that means each day, if I got a ticket one day, that doesn't affect if I get a ticket the next day, and that the probability of getting pulled over each day is the same. So these might not all be true, but that's all we're assuming in just this one simple statement. So back to that framework I mentioned a few slides ago. So our scientific question of interest is, can I get away with speeding? And how we're going to frame this in a statistical way is based on the size of theta. So we'll say if theta, which is the probability of getting pulled over, is really large, there's a high probability I get pulled over, well, then I probably can't get away with speeding. So that's going to be our null. But if theta is small, then I probably can. It's rare that I'm going to get pulled over. And remember, we're trying to prove I can get away with speeding. So that's why we need to put that as our alternative hypothesis, that theta is small. And so here we'll define 0.01 as small. Our test statistic is the number of tickets. And a natural decision rule would be, okay, we're going to reject H naught if t is small. If in a year I only get 0 or 1 tickets, then it's probably I can get away with it. But if in a year I get 100 tickets, well, I might be in jail with that many tickets. But also, I probably should not reject H naught. But how small is small? Is 2? Is 3? Is 4? How small does small need to be? So this is just another question we need to think about. And this is really where p-values and their value comes into play. So let's assume that we're testing this. Theta is 0.01 versus theta is smaller than 0.01. And t is our test statistic. And it's really important that t has some distribution when H naught is true. So we're going to assume H naught is true for this distribution, or for the finding the distribution of t. We'll collect some data and we observe t star. Then the p-value is defined here. And basically, it's the probability of observing a test statistic that's as extreme or more extreme than we did. But the important assumption here is that the null is true. So what's the probability that we'll see the data that we saw, t star, or even more extreme? And so in this case, more extreme would be less than t star, because remember, we're trying to prove our alternative that theta is small. And so you can kind of think of this p-value as evidence against the null, or another way to think of it is kind of a measure of surprise. How surprised were you by this data? If I assumed H naught is true, how surprising is this data? So now I want you to take a minute and just think about, is the p-value a probability or a statistic? And here when I say statistic, I mean a function of the data. So maybe pause the video or take a quick 15-second break to think about this. And hopefully you've paused it by now and thought about this. And you might think probability, it's in the name, right? Probability value, p-value. And well, in a sense, yes, it's a probability. You really should be thinking about it as a statistic. And that's because a statistic is, we know, random. It's a function of the data. So if you collect new data, your statistic will be different, which means your p-value will be different. If we think about p-value as a probability, it implies too much that it's fixed or that it's exactly correct. Whereas when we think about a statistic, we understand it's random. It's a function of this data, and it would be different each time we collect. And so this is really important to think about the p-value as a statistic. So let's kind of put a pin in our speeding example. So we've assumed t is a binomial. And remember, under H naught, we assume theta is 0.01. And we drove for a year and we got 2 tickets, so not bad. So now we compute the p-value. It's pretty straightforward. It's just the probability of this 2 tickets, or more extreme, in that case 1 or 0. And so if you add it up, you get a p-value of 0.29. And so here I kind of graphically show what it means to get more extreme data. The red line is our observed data of 2. And anything to the left of this is more extreme data. So that area is going to be our p-value. Now, this is a little bit misleading, this plot, because we know binomial is a discrete distribution. And so we wouldn't really have these values in between, but it kind of gives a nice picture. And if it was continuous, then it really would be this whole shaded area. So now that we have our p-value, the question is this enough evidence to reject H naught? We've got a p-value of 0.29. And to answer this, we need to kind of understand what are the possible errors I could make in my hypothesis test. And so there's really 2 mistakes we could make. We could reject H naught when it was really true. We shouldn't have rejected it. This is called a type 1 error, and it's usually denoted alpha. We could also fail to reject H naught when it was false. So we should have rejected it, but we didn't. And this is called a type 2 error, and it's denoted 1 minus beta. So alpha is the level of the test, and it's often set to 0.05, but there's nothing special really about this value. It is kind of just a convention. And beta is called the power of the test, or it's the probability of correctly rejecting. And so a good test then would have high power, as a high probability of correctly rejecting, and low error rates. And so what we do is we determine to reject H naught when the p-value is less than alpha. And so we want to balance the type 1 and the type 2 error rates. And usually how we do this is we set alpha beforehand, and that's because alpha is more straightforward to compute, whereas beta can be really complicated to compute. So that's why we're going to set alpha beforehand. And this is an important thing to remember. Remember, so if alpha is 0.05, that means that there's a 5% chance that we'll reject H naught, even if it's true. 5% chance we'll make a type 1 error. So now let's get into maybe one of the more important parts of this talk too, is what are some ways that p-values can be misunderstood and misused. And so this is kind of a long list, but I think it's important to go through each of them and to just kind of have for your reference. So remember, a p-value, it is evidence in favor or against the null. It's not the probability that the null is true. This is probably one of the biggest misconceptions. So a p-value of 0.25 does not mean there's a 25% chance that the null is true. It's just giving you a measure of evidence, a statistic in favor or against the null. And yeah, as we said, it's a statistic. It's random. It'll change every time you collect data. It's not beholden to alpha equals 0.05. This is just a convention. And in many cases, it's probably too lenient. With a lot of research now, people might use 0.005 or 0.0001 or even smaller. So this is definitely just a convention. Another kind of counterintuitive thing about p-values is they're not as helpful for large sample sizes. So usually in our statistics courses, we learn bigger sample size is better, always. And the problem with that, the problem with p-value here is that when n is really, really large, let's say you were testing, your null hypothesis was that theta equaled 0, and your alternative was that theta was not equal to 0. And obviously, theta being exactly 0 is probably really unlikely. Maybe it's 0.01, or maybe it's 0.001. But for huge sample sizes, it's not going to be exactly 0. And so you're going to reject too often, basically. And so that's why for large sample sizes, large, again, it's kind of in quotes, it depends on your context, but for really large sample sizes, p-values are not going to be as informative because they're going to reject oftentimes too easily. Again, this might be obvious, but important to note is that a p-value is not helpful if your assumptions are wrong. If there's model misspecification or something wrong in the steps leading up to this, then your p-value is not going to be very helpful. And the last two, or second to last two, we're going to talk about in a minute. P-values are designed for a single test. They're not designed for multiple testing. And so we're going to touch on that in a minute. But the last thing is that statistical significance is not equivalent to practical significance. So just because your method says your p-value is significant, that doesn't automatically mean there's scientific or practical significance. There's other things that you need to study and understand. And that kind of ties into the p-value is not helpful if your assumptions are wrong. But let's look at the multiple testing problem for a minute. So Let's assume that we're trying to find some new material that has some special property, and we have 100 potential materials to try. So remember, if we want to prove that a new material is better than the current standard, we have to put that as the alternative hypothesis. And then the null is that the material is not better than the current standard. So maybe in this case, our test statistic is the amount of strain before breaking. And we decide we're going to reject if the p-value is smaller than 0.05. So you start running your experiments in the lab, and your 87th material has a small p-value. You get really excited. You declare it significant. You call up Nature, another big journal, and you're pumped. You're going to be famous. You found this new material that solves all your problems. But there's a small problem here. So I want you to think about, again, take 10 to 15 seconds, maybe pause the video. What's the problem with this claim? All right, hopefully you've had some time to think about that. And as we mentioned a few slides ago, hypothesis testing here that we've discussed so far is designed for a single test. And here we're doing 100 tests because we have 100 materials. And so this is called the multiple testing problem. And let's look at this a little bit more thoroughly. So we're going to let pi be the p-value for the ith material. So remember, we have 100 materials, so I will go from 1 to 100. So for a single material or a single test, the probability that we reject I, remember this is under h naught, is 0.05. That's our alpha level by definition. But now what's the probability that if we did 100 tests, we reject at least one? And so we can follow through the math here. And surprisingly, we find out that there's an over 99% chance of rejecting at least one test, even if all of the null hypotheses are true. So another way to put this, there's a 99% chance that at least one of the materials will appear significant, even if none of them truly are. And so this is not great. We have a nature attraction, and it's very sad. So what can we do about this? And so there's many ways to kind of correct for this multiple testing. And again, the problem here is that we're testing multiple hypotheses simultaneously. And this alpha that we discussed is designed to control the error for a single experiment, not simultaneous experiments. So there are many methods that people have to correct in multiple testing. It's actually a very large research field, and a lot of work has gone into. And I'm going to talk about the most popular one, the most intuitive and simplest. It's called the Bonferroni method. And it's named after him because it's based on Bonferroni's inequality. And like I said, this is not necessarily the best method, but in many ways it's the easiest and it's one of the most popular. And so basically all you do, let's say you're conducting M tests, so M was 100 in our example, and you want your family-wise error rate, not just single error rate, but family-wise error rate to be alpha. So then for each hypothesis, I, instead of rejecting if the p-value is smaller than alpha, you reject if the p-value is smaller than alpha over M. Remember, M is the number of tests. So basically all you do is you divide your significance level by the number of tests. So it's really simple, really easy, just one computation. So in our example, if we wanted a level of 0.05, we should have divided by 100. And so we should have rejected if the p-value is smaller than 0.0005, not 0.05. So it's very simple. It's very easy to use. And one important thing to note is that the Bonferroni method can be a little bit too conservative. In other words, it can be too difficult to reject. So that is one of the drawbacks, but again, the advantage is that it's very easy. So just some take-home messages for this part of the talk with multiple testing is that you just need to be really careful when you have multiple tests, and you have to do some sort of adjustment to your p-values. And so we talked about Bonferroni, that's just one of them, but maybe even a bigger message is that in a scientific paper and scientific research, to always report the number of tests you do and all statistical analyses you've conducted. This can really help with some of the issues with reproducibility in research right now. So always report all the statistics you've done. And remember, don't draw conclusions based on p-values alone. There's other considerations that need to go in. And so just some final thoughts. I hope this talk has shown you that every day we're making decisions and there's always uncertainty. And that's what statistics is in the business for, is how can we make these decisions? And it's also quite a philosophical topic. There's a lot of assumptions going into each of our methods and each of our statements. And so it's really important that we carefully understand what we're saying and all of the background that's going into our statements. And with that, we should take our time to carefully construct our hypotheses. And then, of course, use p-values with caution, as we've talked about, and be adjusting for multiple tests. So I thank you for your time, and I hope this video was helpful for you.